this video, we're going to introduce the concepts of covariance and contravariance, which are necessary steps to understand very powerful mathematical objects called tensors that we will be reviewing in the next video.
So this particular video is more like a technical necessity, to define concept that will be used in the next videos, particularly about tensors. I've seen a lot of confusing stuff about covariance, in particular over internet. Now, to really understand what covariance and contravariance are, it's interesting to start with vectors. Each vector is composed of one or more elements called scalars, and scalars are themselves elements of another type of structured set called a field, and usually there are numbers, and it could be real numbers, could be complex numbers, but it could be more than that. Now, a typical example are vectors defining positions of points in space. Here we're looking at a vector in a plane, and therefore with two dimensions. And in this particular example, the scalars are real numbers, but again, they could be complex numbers or any elements of a field in other applications. Now, this vector is defined here with a basis composed of two vectors, x and y. And using this basis, the coordinates of the vector v are 2 and 5, in this particular case. Now, if we change the basis, for instance, here with bigger vectors, bigger vectors means, their amplitudes increased relative to the previous basis vectors. And we can see that the coordinates of the vector will decrease in that case, And of course, if the new basis vectors were smaller, then the vector v coordinates would become greater. So this is why, we say that vector coordinates are contravariant, because it's the opposite from the basis variation. And of course, this is a very informal definition, of course, but that gives a pretty good idea of what contravariance means. But let's get a bit more formal now. The set of all linear forms from the vector space S, defined over the field K, to K is called the dual space of S. It's noted S star like this. Now, in the shown example, we use what is called Euclidean spaces, which means vector spaces, over real numbers with a dot product. But it's also applicable to Hilbert spaces, which are defined over C, the complex numbers. In these types of space with finite dimensions, by the way, the dual space E star of E can be considered as the set of line vectors, corresponding to the column vectors. And this representation assumes that, we selected a basis, of course, which is usually the canonical basis, the one with ones and zeros. And because of these, or thanks to these isomorphisms, we can choose what's more interesting to calculate results or solve equations, And note that we start to see here lower and upper indices, And we'll use a lot of that in the tensor definitions. Now, there is a specific type of linear forms which assign coordinates, and they can be considered as vectors of the dual space. These particular linear forms are merely line versions of the vector representations, So when we use an orthonormal basis, the dual vector is just a transposed version of the vector, for a given basis, of course, again. And so those particular linear forms are defined like this, And so we get this result here. Now, for example, in a 2D vector space with basis B1, B2, we would get this, considering the example we saw before. Now, if we increase the size of the basis vectors, B1 and B2, for instance, like this, then the vector coordinates decrease. And you can see that to calculate vector coordinates in a new basis from coordinates in the old basis, we have to inverse the transition matrix. And I will give a more formal definition and proof at the end of this video here. So, as we've seen before, there are contravariant coordinates. But the basis dual to this basis here will be that basis here. Now, note the indices, which change from down to up here. So the covector coordinates become, 4, 10, and therefore they increase with the change of the basis. And that's why they are called covariant coordinates. And again, I'll give a more formal definition at the end of this video. Now, the main use of covariance or contravariance concepts is in tensor calculus. A tensor is a generalization of a vector. A vector has one index, which explicits its coordinates for a given basis, like this, for instance. A tensor can have more indices and therefore several sets of coordinates or components, whatever you call them, which can be either covariant or contravariant. For instance, if you can define a 3-2 tensor, and it will map 3 linear forms and 2 vectors to a scalar, because it's a linear form. And so we will have 3 covariant coordinates in that case and 2 contravariant coordinates, and it will be noted like this. Now, the use of covariant, contravariant coordinates really simplifies some of the equations in tensor analysis, in particular those using derivatives, which have covariant components. Now, although we've just seen what covariance and contravariance are about, I'd like to formalize the use of these concepts to express changes of frames of reference, which is not always very clear nor rigorous from what I've seen on the web or even in some books. To change from a vector space basis, defined here like this, to a new basis like that, we use a matrix, that we can write like this, such that the vectors in the new basis are equal to this, based on the vectors from the old basis. Now note that the M matrix is built using the coordinates of the new basis vectors, as rows in the old basis. Interesting, and we can see that actually here. Now, any vector, can then be expressed like this, or like this. And using matrix notations, this will yield to that here. From there, I will let you follow the derivation, which is pretty straightforward, and you can pause if it goes too fast, and I will meet you at the summary slide. So here, what I say is the vector coordinates are said to be contravariant. This comes from the fact that they transform the coordinates in the opposite way to the basis vectors. That's why they are called contravariant. So to summarize, to change from a basis E to a basis F, we use the transposed forward matrix that was defined in the previous slides. And we use the backward matrix to calculate the new coordinate from the old ones, And of course, we use the forward matrix to calculate the old coordinate from the new ones. Now, let's see what happens in dual space. And here again, the reason why we call these coordinates from the linear forms, in the dual space, covariant coordinates is because they transform the coordinates in the same way as the basis vectors, as opposed to contravariant coordinates. So there you go. Now you know the real reason for contravariant, covariant terms, and definitions, and why standard vector coordinates are contravariant and their dual covector coordinates are covariant. Note that these covectors are not the only math object which have covariant coordinates. Function derivatives, for instance, also use covariant coordinates, and that's especially interesting in tensor equations. But that's another story.